All right, so today we're going deep on Aristotle,
Right.
like really deep.
Yeah, we're going full philosopher mode today.
But specifically, his views on mathematics.
Mhm.
You think of Aristotle, you think the philosopher.
Right. Big thinker.
But he was surprisingly into math.
Oh, yeah. He was very mathematical.
So we're going to unpack how he looked at mathematical objects, how he viewed those, and trust me, it's way more interesting than it sounds.
What's really fascinating is that for Aristotle, math wasn't just some side interest.
Yeah.
He actually made it a central part of his whole philosophical system.
Oh, wow.
And we see this in his work on physics, astronomy, even ethics, like all over the place.
Okay, so he wasn't just like doodly equations on the side, like while he was coming up with big philosophical ideas.
No, not at all. He had three main ways that he used mathematics. First, he saw math as a model for scientific thinking, like
Wow.
a way to understand the world through logic and deduction.
Okay.
Second, he actually built mathematical arguments into his philosophical ideas, especially in his scientific writings.
Oh, wow. And finally, he developed his own unique philosophy of mathematics, which, I mean, that's pretty bold considering his teacher was Plato.
Yeah.
And, Plato was like a huge figure in mathematical thought.
Wait. Okay, speaking of Plato, now I remember reading that they had some disagreements.
Oh, yeah.
Right, about something called mathematicals.
Yeah.
What was that all about?
Yeah, the mathematicals. This is where it gets pretty philosophically deep.
Yeah.
So Plato believed that, perfect mathematical objects, things like a perfect circle, a perfect triangle, existed in a separate realm.
Okay.
This realm of forms, he called it. And these were like perfect blueprints,
Yeah.
unchanging.
Yeah, okay.
But Aristotle wasn't so sure about all this.
So what were his issues with Plato's mathematicals? Was he just like being rebellious?
Well, he had some pretty strong arguments against Plato's view. One was the problem of precision.
Yeah.
Yeah.
Aristotle argued that, the world is messy. Like a circle you draw, I don't care how careful you are, it's never going to be perfectly circular.
Right, okay, yeah, I see that.
Like perfect circles, maybe those exist in our minds. Good luck finding one in the real world.
Right.
And he also pointed to the problem of separability.
Okay.
Aristotle believed that physical objects are bound to the material world, right?
Okay.
Subject to change, decay. They don't have that, eternal, unchanging quality that Plato saw in mathematical concepts.
So where do they exist then?
Right.
If they don't exist in the real world and they're not separate from it, like where are they?
That's the puzzle.
Yeah.
That's the philosophical puzzle. And there was another problem that likely bothered Aristotle. This is called non-revisionism.
Okay.
Basically, it means any explanation of math shouldn't mess up how mathematicians actually do math.
Okay, yeah.
If Plato was right and math was all about these separate forms, well, maybe mathematicians would have to rethink everything they do. Aristotle was more interested in an explanation that fit with how mathematicians actually practiced, their craft.
Okay. So it sounds like he was finding some holes in Plato's theory. Did he offer up his own solution to this mathematicals issue?
He did. He offered up a solution called extraction.
Okay.
And basically what he's saying is our minds can separate mathematical properties like, say, the circularity of a drawing from the actual object itself.
Okay.
So we can focus on the concept of a circle without, getting hung up on the imperfections of a particular circle.
So like we're filtering out the extra.
You got it. You're filtering out the irrelevant stuff.
Okay, interesting.
He talked about this as like things by removal, where you mentally remove the qualities that aren't important to the mathematical concept.
So if I'm like studying a bronze sphere, mathematically speaking, I'm ignoring the bronze part
Exactly.
and just focusing on like this sphere-ness.
The sphere-ness, you got it. And here's where it gets even more interesting.
Okay.
Aristotle introduces this concept of qua,
Okay.
which is often translated as in the respect that, or like insofar as.
Okay, can you give me an example?
Yeah. So we're not saying the bronze sphere is a perfect sphere, right?
Okay.
But we're looking at it qua-sphere in the respect that it has spherical properties.
Okay, so qua is helping us focus on specific properties, but not saying the object is that perfect thing.
Exactly. And, this addresses some of the problems with Plato's view, like it allows for multiple imperfect triangles to be studied qua-triangle.
Oh.
Meaning, we can have lots of objects representing the same concept without needing these like separate perfect forms.
Okay.
And by using qua, we're sort of treating these mathematical properties as if they're separate from the material object, even though we got them from that object.
Oh, okay, that's interesting.
It's this way of acknowledging the, messy real world while still allowing for this precise mathematical thought.
Okay, I think quaz is starting to click for me. It's kind of like a bridge
Yes.
between the messy world and math.
Yes, exactly. It's that bridge, but I'm still hung up on this. If we strip away all the physical stuff, like you were saying, what's left to make up those individual mathematical objects?
Right. What is a circle made of if it's not made of wood or bronze or anything tangible?
That's the million-dollar question, right?
Yeah.
And this leads us to one of Aristotle's more challenging concepts.
Oh, boy.
This is called intelligible matter.
Intelligible matter.
Intelligible matter.
Okay, I like the sound of it, but I have no idea what it means.
It's a head scratcher. I mean, think about it this way. We've mentally gotten rid of all the physical stuff, like the bronze of the sphere.
Yeah.
But Aristotle thought there was still some kind of non-physical matter that underlies these mathematical objects.
Okay.
And this intelligible matter, that's what lets multiple objects have the same form.
So like a blueprint. You can have one blueprint and build many different houses.
Perfect analogy. Yes, exactly.
Okay.
Now, Aristotle didn't really give us like one neat definition of intelligible matter.
Right.
But the point is, it makes mathematical objects individual. They're not material in the normal sense, but they're not just these floating abstractions either.
Okay. All right, I think I'm starting to get it.
Yeah.
But if they're not material, do they have to be perfectly precise to, like, work in Aristotle's system?
Ah, you've hit on it. You've hit on the precision problem.
Precision
The
problem.
big one. And honestly, Aristotle isn't totally clear on this point.
Okay.
He gives us clues, but we got to do some interpreting.
Okay, let's play detective then.
Yeah.
What clues did he leave us?
Well, one possibility is that he thought perfectly formed objects are out there. They're rare, but they exist.
Okay.
But honestly, that seems unlikely given how much he focused on, the imperfections of the real world.
Right, like why would he build this whole philosophy on something so perfect if he didn't think we'd ever find it?
Exactly. So another possibility is that maybe he was thinking about the potential for perfect forms.
Potential.
Potential. Like a perfect line existing potentially within a, less than perfect line drawn in the sand.
So it's like the bronze sphere could be a perfect sphere.
Yes, it has that potential.
Even though it's not.
Even though it's not. Or, and this is where things get really interesting, maybe Aristotle thought imprecision was okay.
Okay.
Like he recognized that in the real world, we're often working with approximations.
Yeah.
Right. So maybe he thought the precision just increases as you abstract away more and more properties.
Oh, okay. So like the more general the concept, the closer to perfect it is.
You got it. Or maybe he thought greater abstraction meant there were more likely to be actual precise instances out there in the world.
Mm.
So it's a real puzzle. Aristotle, he doesn't give us a straight answer.
Classic Aristotle.
Yeah.
Always leading us with more questions.
Always keeping us thinking.
But before we dive into even more of these fascinating and sometimes frustrating ideas, let's take a break. And we'll come back for part 2 of our deep dive into Aristotle's mathematical mind.
Welcome back. It's funny. For someone who is so focused on the real world, Aristotle spent a lot of time thinking about abstract mathematical concepts, like this idea of universal mathematics.
Universal mathematics. Last time we left off with that, it sounded really interesting, but kind of vague. What was he getting at with that idea?
It gives us a glimpse into how mathematical thinking was evolving back then. In the Posterior Analytics, Aristotle talks about how mathematicians were starting to look beyond just proving things separately for different types of quantities, like numbers, lines, planes, solids.
Oh, so instead of proving a theorem for lines and then proving it again for solids, they wanted something more general, an approach that would work for everything.
Yes, exactly. Universal proofs that would apply to all kinds of quantities. And he even mentions they'd already made some progress in this area, especially with theories of proportion. You can see how this kind of thinking led to what we know today as algebra.
Yeah, it sounds a lot like modern algebra, where we use letters and symbols to represent any quantity. It could be a number, a length, a volume, whatever.
That's exactly right. It was a huge leap forward. But as with a lot of things, Aristotle also saw a potential problem.
Uh-oh. What kind of problem?
Well, remember how we talked about Aristotle's idea that each science has its own subject matter, its own genus?
Yeah, like biology is about living things. Physics is about motion and matter.
Right. So he struggled with what the genus would be for a universal mathematics. If it included both continuous magnitudes like lines and discrete quantities like numbers, what exactly is it studying?
Yeah, I see what you mean. That's a tough one. It's like trying to find one category that fits both apples and oranges. Sure, they're both fruits, but they're also really different.
It's a real head-scratcher. Aristotle doesn't give us a clear answer, but he offers up some possibilities. One idea was a higher-level science of posology.
Posology. Now, there's a word I haven't heard before.
Yeah, it's not one you hear every day. Basically, it would be the science of quantity in general, looking at what all quantities have in common, no matter what they are specifically.
That's really ambitious. It's like trying to come up with a theory of everything in physics.
It is, and he also suggested that maybe these universal proofs work by analogy. Like you might see similar patterns or structures in how proportions work, whether you're dealing with lines or numbers, even if you can't directly use one to prove the other.
I see. So it's like recognizing a family resemblance between different mathematical concepts, even if they don't have identical DNA.
That's a great way to put it. But unfortunately, we don't have any evidence of a fully developed Aristotelian universal mathematics in the surviving texts from ancient Greek mathematicians.
So maybe it was an idea ahead of its time. Or maybe it's a challenge for mathematicians today to try and develop such a system.
It definitely deserves more attention. But for now, let's shift gears a bit and explore another area where Aristotle's mathematical thinking shows up: his ideas about place and the continuity of magnitudes.
Okay, I'm ready for a change of scenery. But first, remind me, why was Aristotle so interested in place and continuity?
Well, it goes to the heart of how we understand the physical world. Remember how we talked about Aristotle being a bit more grounded than Plato?
Yeah, less about those perfect, otherworldly forms.
Right. He was really interested in how mathematical concepts connected to our actual experience of the world.
So he was trying to make math work in the messy reality we live in.
Exactly. And that focus led him to some interesting ideas about the nature of space and the stuff that occupies it.
Okay, tell me more. What kind of ideas?
Well, the main thing to understand is that Aristotle had a different view of space than we do now. Today, we think of space as this empty container that things exist in.
Right, like an empty box.
Yeah. But for Aristotle, place was more about the limits or boundaries of a body.
So instead of a box with stuff inside, it's more like the stuff itself is defining the space.
Yes. That's a great way to put it. So, for example, the place of a fish would be the water surrounding it, because that's what defines its limits. And he extended this idea to all physical objects.
That's a very different way of looking at space. So how does this connect to his ideas about continuity?
Well, remember how we talked about Aristotle not liking the idea that lines are made up of indivisible points? That was a big debate back then in ancient Greek mathematics.
I vaguely remember that. It's hard to picture a line made up of points because points don't have any length. But how else can you build a line?
Exactly. It was a real puzzle. Some people thought lines must be made of a finite number of tiny, indivisible pieces. Others thought there must be an infinite number of points. But both options led to all sorts of paradoxes and problems.
Yeah, I can see how that would get messy fast. Trying to wrap your head around infinity is already hard enough.
Right.
But then trying to figure out how an infinite number of points make a continuous line. That sounds like a recipe for a headache.
You got it. Aristotle rejected both of those views. He said lines are infinitely divisible, meaning you can keep cutting them into smaller and smaller pieces, but they're not made up of an infinite number of points. He used this concept of potential points to explain it.
Potential points. Okay, this sounds like another one of those head-scratcher ideas.
Think of it like this. Imagine you have a perfectly smooth block of marble. It has the potential to be sculpted into lots of different shapes. But those shapes don't actually exist until a sculptor chisels them out.
Okay, I'm following so far.
So in the same way, Aristotle thought a line contains an infinity of potential points. You can divide it anywhere along its length. But those points only actually become points when you actually make a division.
So it's like saying the line has all these points and waiting, ready to become real if you cut the line at those spots.
Precisely. And he said the continuity of the line comes from the fact that any point you create, by dividing the line, will hold together the two line segments on either side of it.
So even though the points aren't real until you cut the line, they have this power to connect the pieces back together, like a hidden glue that keeps the line continuous.
That's a great analogy. It was a really clever way to solve this problem of continuity. It avoids those paradoxes that come with actually having an infinite number of points making up the line, and it fits really well with his whole philosophy of emphasizing potential.
Yeah, I'm starting to see how these different pieces fit together. Abstraction, intelligible matter, potential points. It's like he was building a whole new framework for understanding how the physical world and the abstract world of mathematics relate to each other. Pretty amazing when you think about it.
It really is. But it's important to remember that Aristotle's ideas weren't universally accepted. There were other philosophers and mathematicians who had different views. And even today, there's still debates about these fundamental questions, the nature of space, continuity, the foundations of math.
That's what I love about philosophy. There are always more questions to explore, more perspectives to consider. Speaking of different perspectives, I think it's time to bring Plato back into the ring. Last time we focused on Aristotle's criticisms of Plato's mathematicals. But what about Aristotle's own positive views on numbers and units? I think that's a good place to pick up next time. Okay, round 3 of Aristotle versus Plato. This time it's all about units and numbers, the building blocks of math.
And even back then, this got pretty complicated. They understood numbers as collections of units.
Right, like having a pile of pebbles for 5 or a line divided into equal segments.
Exactly. But then you run into some big philosophical questions, like what exactly is a unit? What makes a bunch of them into a single number? Are they like Plato's forms, perfect and unchanging, or something totally different?
Ah, yes, the classic debate. Are numbers something we discover or something we invent? I bet Aristotle and Plato had some thoughts on this.
They definitely did. Aristotle knew about all the different theories going around, a lot of them coming from Plato's Academy.
Oh, lay it on me. What were the ancient Greeks coming up with?
One theory was all about these incomparable units. You know how we use different units to measure different things? Like you wouldn't measure time with inches?
Right, you use seconds, minutes, hours.
Exactly. So some thinkers thought numbers themselves were kind of like that, inherently different. They thought numbers were basically ordinal, meaning their most important feature was their place in a sequence.
So it's not how many units you have, but where they are in line. That's pretty abstract.
It is, and it creates some problems, like how do you add or subtract if numbers are just positions in a series? How do you add the third position to the fifth position? Doesn't really make sense.
It's like trying to add apples and oranges again. Both fruits, but you can't combine them into one superfruit.
Haha, exactly. Then there was another theory with comparable and incomparable units.
Okay, this sounds even more complex.
It is a bit more complicated. Basically, it says that the form numbers, the perfect ones in Plato's world, were made up of unique, incomparable units. You couldn't mix them with units from other form numbers.
So each perfect number had its own special set of units, like a VIP club just for that number.
You got it. And then they had these other units, comparable ones, and you could combine those. That's how they explain how we do math with regular, non-form numbers.
All right, so we've got elite numbers with their exclusive units and then normal numbers with more flexible ones. Seems like a lot of work. Did Aristotle buy into any of this?
Not really. He thought these theories missed something important about numbers, what we call the unity problem.
The unity problem. Remind me what that is.
It's the question of what makes a collection of units into a single whole. Like, what turns a bunch of pebbles into the number 5? Is it just because we group them together in our minds, or is there something more to it?
Yeah, it's like, what makes a team a team? Is it just being a group of people, or is there something more that makes them a unit?
Exactly. Aristotle thought the answer was measure. He said that numbers are always numbers of something, a way of measuring a specific quantity.
So it's not just 5, it's 5 apples, or 5 miles.
Precisely. And that unit of measure, that's what makes the number a single thing. 5 apples are unified because they're all apples. That's what ties them together.
Okay, I see how measure solves the unity problem. It gives all those units a common ground. But what about the question of perfect, unchanging units? Was Aristotle on board with that like Plato was?
Well, Aristotle was a little more down to earth, you could say. He thought the precision of a unit depended on what you're measuring. If you're counting things like cows, the unit is very precise, 1 cow. But if you're measuring something continuous, like time or distance, the unit's a little more flexible, depending on how exact you need to be.
So it's like using a ruler with different markings. You need a rough idea, use the inches. You need to be super precise, use the tiny fractions of an inch.
Perfect example. And Aristotle thought that mathematical units, like the ones in geometry, are precise because we got them from the real world but made them abstract. We stripped away all the extra details and kept the core unity and being indivisible.
Like we took a cow and boiled it down to pure cowness to get a perfect unit of 1.
That's a great way to put it. And this brings us to maybe Aristotle's wildest idea, that there's no number without mind.
Hold on, are you saying numbers only exist in our heads?
Not exactly. He believed numbers are real, but they need a mind that can count and measure to, make them make sense. It's like that question. If a tree falls in the forest and no one's around, does it make a sound? Aristotle might say if no one's there to count, there's no number.
I like that analogy.
Yeah.
So numbers are out there, but they need a mind to see them and understand them, like a potential waiting to be fulfilled.
Exactly. And that goes back to this idea of potential that's all over Aristotle's work. The world is full of possibility waiting to happen. And the human mind, because it can abstract, measure, understand, it's part of making those possibilities real.
Wow, it's really been a journey into Aristotle's mind. He was a true original, bridging the gap between those abstract ideas and the concrete world we live in.
He definitely made us rethink numbers, units, and what role our minds play in math, and his ideas are still sparking debate today.
So the big question, was Aristotle right? Are mathematical objects discovered, invented, or somewhere in between?
Oh.
We'll leave you to ponder that one. Thanks for joining us in this deep dive into Aristotle's mathematical mind. Until next time, keep exploring those big ideas.